So check out this question. It's number 1 off the WebAssign. A 5 kilogram box is sitting on the floor at rest and it's connected to a rope. The coefficient of static friction between the box and the floor is 0.5. We'll talk about what this symbol means. The coefficient of kinetic friction between the box and the floor is 0.3. It says for the given values of tension in the rope, give the magnitudes of the force of static friction, kinetic friction, and the acceleration. So there's basically 2 kinds of friction, static friction and kinetic friction. And static friction happens as you're trying to pull this thing. This tension right here, this tension right there, these numbers is how hard you're pulling the rope. And so as you're pulling with weak forces, there's enough grippy static friction to prevent this box from moving at all. It just doesn't budge. Once your tension gets to a large enough force, the static friction is going to be like, all right, you know what, forget this. I can't do this anymore. It'll start to budge. It'll start to slide. And once it's slipping, once this is sliding, the 2 surfaces are sliding across each other, you'll have the other kind of friction, which is kinetic friction. But you can only have one or the other because it's either slipping or it's not slipping. And so if you've got static friction, kinetic friction is going to be 0. And if you've got kinetic friction, then the static friction is going to be 0. Which way do these point? Well, we know what forces we've got. We've got a force of gravity, straight down, Fg. We've got a force of normal, Fn. And in this case, is the normal force going to be equal to the force of gravity? Yeah, because there's no extra vertical forces. It's just sitting on a flat horizontal surface, and there's no vertical acceleration going on. So these 2 will be equal and opposite. They're balanced. And then we've got this tension force forward. We've got this T. And here's the deal. We'll have a static frictional force, and the kinetic frictional force, when that happens, will be in the other direction. It's always opposing our motion. And static friction is kind of weird because it'll just equal whatever we pull with. So if I pull with 6.125 newtons and it's not budging, that means static friction is just pushing the other way with 6.125 newtons. It exactly matches it. And if I pull with 8.1666667, then static friction will just match that. It'll just bump it up. And if I keep adding a little extra force, static friction adds a little extra force, whatever it needs to do to keep this thing from budging, to keep it from slipping. And then once it budges, the static friction goes away. So how do we figure it out? Basically, what we need to figure out is what is the maximum possible static frictional force, right? If we knew this number, let's say it was like 15, then if we pull with 12.25, the force of static friction would be 12.25. But once we pull more than that, this box will budge and we'll have no more static friction. We'll just have kinetic friction. So how do we figure out this number right here? There's a formula. It says that the maximum possible grippy static frictional force, the most this thing could ever oppose you pulling on it with, is equal to this coefficient here. It's called mu. This is the Greek letter mu, like Mewtwo, but it's not. It's just the Greek letter mu. Don't draw it as an M. I don't want to see M on there. Draw it the right way. If you like, think of it as like a U, and it's got a cape. Give it a cape. It's flying through the air. Mu S, so the maximum static frictional force is equal to mu S. That's what this number is here, 0.5, times the normal force between the 2 surfaces that will have the grippy friction. And that's it. This is the formula that gives you the maximum possible static frictional force. Mu S is a measurement that depends solely on the 2 surfaces involved. So if you've got box here, this box is made out of certain material, maybe it's made out of iron, or maybe it's an ice cube. I like that. You're pulling on an ice cube. This is an ice cube and it's sitting on wood. Let's say the surface of this table is wood. If you know what these 2 surfaces are made out of, you know this number. I mean, you can look it up. You guys don't have these memorized. I don't have them memorized either, but you look them up online if you had to. You're not going to have to, because I'll either just give them to you, or I'll give you enough information that you'd know everything else and you could just solve for the only unknown. But the important thing is that this number only depends on what the type of materials are. It doesn't depend on how much normal force or how much you pull or how much anything else in here. Once you know what the 2 materials are, this number is determined. And then the other thing that the maximum static force depends on is the normal force. Obviously, if this mass was really heavy, or this ice cube, just massive ice cube, had a bunch of weight, then these 2 surfaces are getting pushed into each other a lot. There's going to be a lot more grippy friction happening there. So you can either, what I'm saying is you can either get a really big maximum possible static frictional force if you push these two surfaces together, we know that. And if they're inherently grippy surfaces, ice, it's going to have a really low mu-s. So this is probably a bad example, sorry. Ice would probably have a mu-s of 0.2 or something against another surface. And it's important to note that you have to specify both surfaces. I can't just say, what is the coefficient of static friction? That's what this mu-s is, the coefficient of static friction. I can't just ask, what's the coefficient of static friction of ice? Because ice on what? Ice on wood, ice on metal, ice on anything. You can imagine any possible scenario. You have to specify both. This would be the coefficient of static friction between the ice and the table. And I want to stress, if I push down with some extra force here, I'd be increasing the normal force, and that would increase the maximum possible static friction, but it would not change mu-s. Mu-s depends entirely on the two surfaces, and that is all it depends on. All right, so let's do this problem then. Let's try it out. So what do? We should find this number. So for this problem, the maximum possible static frictional force is going to be 0.5. Notice this does not have any units, no units for mu, and it's because if you rearrange it, you'd find out mu-s is Fs maximum over Fn. It's the ratio of the maximum possible static frictional force over the normal force, and that'd be newtons over newtons, which cancel, and you leave nothing but a ratio, and so that's why it has no units. Times the normal force, what's this going to be? Well, we said the normal force here should be the same as the force of gravity. That's nice. It won't always be like that, but in this case it is. So 5 times 9.8, not 9.8. People sometimes want to say the normal force is 9.8 or the force of gravity is 9.8. Force of gravity is m times g. So you multiply all this together and you get 24.5 newtons. So let's come down here. What's the force of static friction if my tension is 6.125? A lot of people are like 24.5 newtons, but think about that. You're saying, okay, I pull with 6 newtons. You're saying the force of static friction backwards would be 24.5 newtons. That means I'd pull a little bit and this box would go the other direction. That makes no sense. That's what happened. It's not 24.5. What we found up here is not the force of static friction. What we found is the maximum possible force of static friction. Static friction is just going to equal whatever you do until you reach this maximum. This number doesn't tell you what the value of the static friction will be. It just tells you the maximum value. So in other words, if I pull with 6.125, I know what happens. I haven't reached this value yet, so it's just gripping. And static friction is going to match whatever I do. So this would be 6.125. How about this one? Again, I'm not at this level yet. I'm not pulling at this level, so friction can oppose whatever I do, and it's just going to match whatever I do. So this would be 8.1. You don't have to write so many sixes. WebAssign got a little squirrely there. Sorry about that. How about 12.25? Still not at this level. These are all, the force of static friction's going to match whatever I do until I get to, let's see, 24.01. Still not strong enough. 24.99, okay, finally I'm above this value. So if I pull on this string with a force greater than 24.5, static friction gives up. It's like, fine, you win. And now it starts sliding. And since it's sliding, we don't have any static friction. All these are 0 because it can't be static friction if the thing is sliding, excuse me. So if it's sliding, there's no static friction. How about the force of kinetic friction? Well, this only exists. You will only have kinetic friction if the object is sliding. So static is when it's not sliding, it's gripping. Kinetic when it is sliding. So if it's gripping, it's not sliding, there's no kinetic friction. Remember, you can only have one of these or the other. But once it starts sliding, how do I figure out this number? How do I figure out the force of kinetic friction? The formula looks very similar. The formula for kinetic friction says Fk equals mu k Fn. So this is the coefficient of kinetic friction, which we're given up here is 0.3, and it's always less. So it's important to know. Mu s is always bigger than mu k. And you've probably realized this. When you go push on something really heavy, it takes a lot of force to get it to budge, and then once you get it budged and it starts sliding, you can keep it sliding a little bit easier than it was to get it moving in the first place. So this mu k is 0.3, and it's less than 0.5. It has to be. And Fn, we know what Fn is. It's 5 times 9.8. So if I multiply all of these together, you get 14.7 newtons. Now, kinetic friction is a little bit different from static friction. This formula only gave you the maximum static friction, but this formula for kinetic friction actually does give you the value for the kinetic friction. If it's sliding, this is the value. So once it starts sliding, kinetic friction just does what it does regardless of how much you push. I don't care if you pull or push with 49 newtons or 122 newtons. Kinetic friction is just like, man, I'm just going to do what I want. I don't care what you do. Static friction was the one that just matched whatever you did. Kinetic friction always just stays the same. So this is just the value of the kinetic friction. If there is kinetic friction, this is what it is. So how do we find this acceleration over here? Well, the first few are easy. If I got static friction, I'm trying to pull this box, and there's static friction, that means it's gripping it. And if it's gripping it, I got no acceleration. This thing isn't even sliding yet. So no acceleration here. Once I have kinetic friction, okay, this thing's sliding. It might be accelerating because this tension force might be larger than the force of kinetic friction, and the kinetic friction would also go backward. It wouldn't exist at the same time static friction did. But once it does exist, if it's smaller than this tension, I have an unbalanced force. I could have acceleration. How do I find it? You know how to find acceleration. Just do Newton's second law. A in a given direction, and this time we want x, equals the net force in that direction over the mass. What's my net force? Well, in the x direction, I've got t minus the force of kinetic friction. It's sliding. I'd want kinetic friction, which was 14.7 always, no matter how hard I pull. 14.7 if it's sliding over the mass, and the mass was 5 kilograms. So 5 is the kilograms. I plug in my t. So for this one, I take this t number, 24.99. I plug it into there. 24.99 minus 14.7 over 5 gives me 2.058 meters per second squared. And then for the next one, okay, now I'm pulling with 36.75. That's my new tension. So 36.75 minus 14.7 over 5 gives me 4.41 meters per second squared, and so on. I'd plug in 49. I'd do the calculation. I'd get all of these. So that's how you do this one. Again, force of static friction, this formula gives you the maximum value. Let's look at another problem. Let's try this one out. All right, let's get a hard one. We'll jump right into it. Check this one out. Box of mass 14 kilograms sitting on a table. Someone's also pushing on the box with a force of 150 newtons at an angle of 18 degrees. The coefficient of kinetic friction between the box and the table is 0.15. We want to know what the normal force is and the acceleration of the box across the table. All right, what do we do? First thing we do, I don't care if it's a new force, you draw a force diagram. So what do we got? We've got gravity straight down, Fg. We're going to have normal force up. This time normal force is going to be bigger than gravity. It's going to be bigger because we're pushing down a little bit extra. This Fa, I'll redraw it because it should be in my force diagram. This Fa has a downwards component of force, pushing down. And we know the vertical forces have to balance or this would crush through the table. And if this box is sliding across the table to the right, because this has a rightward component, then there's probably going to be an Fk value, a force of kinetic friction to the left. So those are my forces. Let's try to figure out what the normal force is. To do that, you know what to do. We use Newton's second law in a direction that we care about. This time we want to find the normal force. Since that's a vertical force, we'll use Newton's second law in the vertical direction, which says the acceleration vertically is the net force vertically divided by the mass. What's the acceleration vertically? That's 0. This box isn't flying up or down, so that's 0 equals what goes on top for net force. One vertical force is Fn, and it's pointing up, so I'm going to leave a positive sign out front. Another vertical force is gravity, so minus mg, the mass is 14 kilograms, so I'm going to put 14 times 9.8. And then minus this component. This Fa has a downwards component. How big is that going to be? And it's going to be negative because it points down. Well, Fa has a size of 150. So this hypotenuse is 150. That means this side, if you do the trigonometry, is going to be 150 newtons. Look at, here's my angle. This is opposite of that angle. That means it's 150, the hypotenuse times sine of this angle, and that angle it says is 18 degrees. So minus 150 sine of 18 degrees. We divide by the mass is 14 kilograms. All right, now we solve for Fn. Multiply both sides, we still get 0 on the left. And then if you move everything over, do the algebra carefully, solve for Fn, you get 183.6 newtons is the normal force. So that's what this normal force is, 183.6. What's the acceleration of the box? Well, it's not accelerating vertically. It's going to accelerate horizontally. So we got to do Newton's second law in the horizontal direction. A in the x direction will be the net force in the horizontal direction divided by the mass. The net force, all right, what forces do we have horizontally? We have this piece, this horizontal piece of this FA, and FA is 150, so that piece is going to be 150 cosine of theta, because this piece is adjacent to that theta, so 150 cosine of 18. And then minus Fk. How do we figure out what this Fk is? We've got the formula. We know it's mu k Fn is what Fk is. And so if I plug in mu k was 0.15. So this force we can solve for. A lot of forces, we just have to stick their name into the Newton's second law and just solve for them. But for the kinetic frictional force, we can actually figure out what they are. So 0.15 times the normal force, we figured that out, 183.6. And if you multiply all that out, 27.54, I'll put that over here, 27.54. I divide by my mass, which was 14 kilograms. And if I multiply all that out, I get that the acceleration is 8.22 meters per second squared. So that's what you get over here, 8.22 meters per second squared. So in this problem, the normal force was not mg, so you had to be careful. You couldn't just plug mg in for the normal force because there was an extra vertical force pushing on this thing. And other problems will be tricky too, so check out this one, not that one, this one. Box being pushed into a wall. Now the normal force, which is going to point to the left, is not even going to be in the vertical direction at all. So you're going to have to do Newton's second law in the horizontal direction in order to find the normal force. Then use that normal force in the friction formula to get the friction. All right, so please spend the rest of class